It's here.
A full torso apparition, and it's real.
So what do we do?
Welcome to the Expanding Universe. I'm Jesse Rogerson.
I'm Ryan Marciniak. Let's get right to it. So the question we're talking about is, when I look at stars, are they already dead? So when I look at the stars in the sky at night, are they still alive? Are they ghosts? Right? People talk a lot about ghosts in the sky.
And you know, I've seen this in countless, well, maybe not countless. I've seen this in movies. I remember watching either TV shows or like movies of some kind where someone points up and goes, "Hey, you know, when you look at the stars, they're actually already gone, and the light's just still traveling to us." And in my head, I cringe. I'm like, "No, that's not true." So it's out there. The question is out there. People talk about it as the stars are already gone and we're just looking at the light that's still traveling to us. And it sounds cool. It sounds like space is big enough for that to be true.
Well, yeah, you know, when you do observing nights, and I know when I do observing nights, people are always saying to me, like, "Oh, is it true that some of those stars might not be there anymore?" Like they almost say it with this kind of reverence of the universe. And I mean, that is really cool. We all have a reverence for the universe.
Yes, reverence for the universe is correct.
But having the reverence of the universe for the correct reasons is kind of important. So I guess we're kind of hinting at the answer is that when I look at stars, are they already dead? Well, no, they're still alive.
They're all still there.
Yeah, every single one. And most of them aren't even close to dead.
I would say
scale of time.
Okay,
right?
well, it depends on how we. So now we should frame the question a little bit more, right? So when you look at are you talking with the naked eye? So when you go out and you look up into our night sky, you see a few thousand stars with your eyes alone, and if you were to use a telescope, you'd see many, many, many more. Now, the few thousand that you see with your eye alone are pretty darn close to us, galactically speaking, within the galaxy that we live in. So I guess we're the question really is with the naked eye, right? That's usually what people mean.
Yeah, I think most people's view of stars, most people's version of looking at stars is being out there and with somebody they love and just looking up, and there it is, there they are. Those are the ghosts, right? Those are the ghosts in the sky. So yeah, I think we just keep it to the stars that we can see with our eyes. And I mean, in the city, that's, you know, maybe 100 tops.
Yeah.
But in the country, that can be 1,000. So let's say an appropriate night sky with an appropriate set of human eyes with decent vision can see maybe 1,000 stars. And we know that those stars have different colors, that some of them are different sizes, and they're all different distances from us.
So let's put that in perspective.
Yeah, we're already saying that they are not dead. None of them are dead.
None of them. So let's put it in perspective in terms of sizes, or in light travel time. Should we talk about light travel time?
Sure. What is a light year? If I say a star is 40 light years away, what does that mean? It's not a unit of time, right?
Right. It's a unit of distance. Light. It sounds like time because it has the time, the day, or sorry, the word year in it. But it's light travel time. It connects to a distance. And the easiest way to think about it is that light takes time to get places. Like when you're looking at your friend on the street, you see light bouncing off of them from the sun and coming to your eyes, and it takes time for the light to get from the person that you look at into your eyes, and that you're just so close to that person that it seems instantaneous because light travels so quickly and the distance is so small.
Like flipping on that light switch, right? You turn on a light switch and the light fills the room instantly.
It
but
feels
it's not.
Yeah,
but it's not, right? It's happening so quickly that our slow, lazy eyes can't actually pick that up, right? But being on a beam of light, though, you can go far. And in 1 second on a beam of light, you can go all the way around the Earth 8 times.
Yeah, that's crazy.
That's a lot of distance.
Yeah. And to the moon?
300,000 kilometers per second.
The speed of light, 300,000 kilometers per second. And so 8 times around the Earth in 1 second. And to the moon, it takes about a second and a half, right?
Yeah, that's, a long trip, right?
Right. And then and then to the sun, to our sun, it takes 8 minutes to 11 seconds. So light travel time of 8 minutes, 11 seconds. And we would call that a distance of 8 light minutes.
I love that too, especially with the sun, because when I tell this to people, the instant response is, so wait, we're like seeing the sun in the past.
I know.
And of course, my next response is, yeah, hey, the sun could have exploded in the last 8 minutes, and we have no idea.
You experience the entire universe in the past.
Yes, you do. And the deeper you look, the more you experience it in the past. Okay, we're getting too far off the point here. So we've got 8 light minutes to get to the sun. And
what's next?
That's 150 million kilometers.
Right. And what would be the next waypoint after that? The edge of the solar system?
Sure, yeah.
So that's 5 light hours in distance to get to, say, Pluto?
Yeah.
So it takes 5 hours of light travel time for the light to get from the sun to Pluto. And so we call that 5 light hours.
Which doesn't seem that far when you say, oh, it's a 5-hour trip.
It does for light, yeah.
Like a 5-hour trip is a long way to a cottage, but it's reasonable in a day. But that beam of light, 5 hours is what, 3 billion kilometers out to Pluto?
Yeah, and it took New Horizons how long to get there? 7 years.
Yeah,
so
I think it was 9.
The spacecraft that flew by Pluto took years to get there. So the difference in speed there is astounding. And now is when we start talking about the jump to the next star. So how far is it to the next star?
Oh, it's 3.6 light years.
3.6 and 4.2?
Oh, 4.2. I don't know why I'm thinking 3. Oh, for the Alpha and Proxima Centauri?
Yeah.
Yeah, I think so.
Aren't they? I don't know. I thought they were.
We'll fact check that. But we like to say basically 4 light years, because it's a nice round number, like it's really even 3.6 or 4.2 light years is not precise enough to really say like, oh, that's what it definitely is. It's actually a few 100 million kilometers more or less than that. So
yeah.
So we'll say 4 light years I think is reasonable, which means traveling at the speed of light, traveling on that light beam, going around the Earth 8 times in 1 second. If you could travel that fast for an entire year, that's 1 light year and a huge amount of distance. And of all the stars in the sky, those thousands of stars that seem like they're just, a couple kilometers out, the closest one of those is 4 light years away, 4 years at that crazy fast speed.
So that in my head leads to the question. The question we began with is, are the stars I'm looking at still there, or did they die while the light was traveling to me? Now, if it was Alpha Centauri, Proxima Centauri, 4 light years away, that means that for it to have died en route to us, it had to have been very close to the end of its life, within 4 years of the end of its life, so that it died while the light was still coming to us, right? And so that the question then becomes, how likely is it that it's that close to the end of its life?
Well, if you look at most people, they would say, wow, 4 years is a long time. 4 years out of my life is a pretty big chunk. I mean, 1/25th if you live to be 100. So that's 1/25th of a person's life is pretty significant. But I think most people know that stars live a lot longer than you or I.
Yes, much longer. Depends on the star.
It definitely depends on the star. Well, what's the general rule of thumb, right? Larger stars burn through their fuel faster, and so they die sooner. They don't live as long. Bigger, more massive stars don't live as long. Smaller, low mass, low energy stars live much longer. In some cases, longer than the universe has already been around, which is a whole other story. But how about the sun? What's the lifespan of the sun?
Well, we think it's 10 billion light years. Or sorry. We think the age of the sun is 10 billion years.
Okay, this one's actually a unit of time, right? 10 billion years at 8 light minutes away.
It's ridiculously long, like for humans to understand, to comprehend the length of time that a star is around.
Well, even the Earth being around, right? We talk about, the asteroid falling in Chicxulub, Mexico, that killed the dinosaurs, and that was what, 70 X number million years ago, 70 million years ago, and like we're just like, oh yeah, that's just 70 million years. That's barely anything. Right? That was just like yesterday. 70 million years is a ridiculous amount of time for a person who lives to be 100 years old. That's 1,000 lifetimes, or is that 10,000?
It's a lot of lifetimes. I mean, we aren't built to comprehend this kind of thing. Our minds aren't built to really think about times longer than really 50 years. I mean, when do you really start really comprehending long duration time? So
we don't. That's why. So we have scientific notation, so we can get a feel for these ridiculously large numbers.
Yeah. So the Earth is 4.5 billion years old. The Sun is roughly that as well, and will live another 5 billion. These are long time frames. So if you can just take that right there. So if you take the Sun as 10 billion years old, what's the likelihood if all the stars in our galaxy are roughly the same as the Sun, then say you put the Sun at where Alpha Centauri is, what's the likelihood that it died in the last 4 years?
Or will die within the next 50 years or 100 years, so that you'll see it in your lifetime. Oh yeah, it's like vanishingly small that that a star has died. Yeah, being within 4 years of the end of a 10 billion year lifespan is almost near zero. So now that's for the Sun, and we know the Sun is a pretty average star. It's not super huge, and it's closer to small. It doesn't output as much energy as a lot of these gigantic stars. But when you look at the largest stars that you know of, they don't live very long. They live less than 1 billion years. They live about, what, 200 million, 250?
Yeah, I've seen like quotes anywhere from like 100 to 500 million years old, or in total length.
Do you know the Pistil Star? Do you know what that is?
No, I don't. What's that?
So the Pistil Star was the largest known star for a while. It was like the most luminous star in the galaxy. It's very close to the galactic core, and it's a blue supergiant.
I've never even heard of it.
Yeah, look it up. It's really neat. It's
I'm Googling it right now.
I see it in a lot of comparison videos of the sizes of stars because it's a good thing to talk about. Like, oh, the Pistil Star is the most luminous star in the galaxy, and it's this big. And then there's this other star that's red and cooler and doesn't output as much energy, but it's way bigger. So they use it as
it's
kind of
300 times the size of the Sun in terms of like diameter.
Yeah. Which is pretty crazy, and that's a lot, but there's stars that are far larger than that too. So the thing about the Pistil Star was that being the most luminous star in the galaxy, it's going to burn through its energy faster.
Super
right?
quick.
If you're driving a Hummer, it's going to burn through gas a lot faster than
that's a good analogy.
Than a little bug, right? Volkswagen
so yeah,
Beetle.
good. I like this. Is a good way to think about stars. Is the big, huge, bright stars are like Hummers. And the little stars, the red dwarf stars, those are like Priuses.
Oh, that's even better.
Yeah,
yeah, and they don't even no electricity, whatever. So yeah, they go through their energy so much slower, and even the Sun. So the idea was that the Pistil Star, being the Hummer or the transport truck of stars, its life was only supposed to be about 50 million years. Which is
wicked short.
Right, very low, and so that's probably the lowest estimate I've ever heard for the life of a star.
Yeah,
any star. So I know most blue supergiants, the most luminous stars, even like Wolf-Rayet stars, are probably around 200 million. So I think getting to the short end of star lifetimes, the ones that live fast and die young, they're maybe 250 million years, I think, is a reasonable estimate.
Okay, so then by that logic, for the likelihood to be high that a star has died while the light is still coming to you, it needs to be roughly that same distance away as its total age. So if a star is going to live to be 100 million years old, then it needs to be roughly 100 million light years away in order for it to have a chance of dying while it's coming to you because it takes that long for the light to get to you.
Yeah, I mean, because you're still seeing it, but we can't. I mean, we see stars that are that far away in galaxies with big telescopes, but most of the stars in our galaxy, or at least the ones we were talking about that you see in the night sky, are much closer. Like, what do you think is the farthest star that we can see with our eyes?
Oh, that's a good question. I have no idea.
Well, and that might be one to treat later on as we continue on with the show.
Okay, I'm going with a guess of 5,000 light years.
Yeah, I think that's reasonable. I mean, I don't know the exact answer, but I think that's a reasonable answer. If you look at the bigger stars, the brighter ones, like Betelgeuse, right? Bright red star in Orion.
Beautiful. Is
700 light years distant. I think 600 or 700. Actually, I'm going to look that up because I'm not sure.
Well, and that's an interesting one right there, because Betelgeuse is actually on the edge of dying.
642 and a half light years. That's not bad. I'll take 600 to 700. So you're right, though. It's on the cusp, isn't it?
Yeah. So Betelgeuse is one of those stars that has been around for a very long time, and the way it's acting makes it seem like it might explode sometime soon as a supernova. It's big enough to do that. So that one actually, although again, I mean, it's only 600 and something light years away. That means that it needs to be close to 600 years before it dies for it to die while the light is coming to us. So it's like, it even still seems pretty, for when a star has billions of years in age, for it to be within a few hundred years of dying just at that moment you're looking at it is still vanishingly small.
Well, and then here's the next thing. So, like, let's say, for argument's sake, that Betelgeuse did explode as a supernova and died 400 years ago.
Okay.
That means it's got about 242 and a half years left until that light reaches us. That still doesn't mean anything to us. 250 years until that supernova reaches us. Like, everybody on Earth is going to be gone by the time that actually gets to us. So
yeah.
And that's close. And that star is the ghost, right? That if that was the one if that died in the last 600 years, that is that rare case where, yeah, that star that you're looking at is already dead. But the problem is there's no way to know that until the light reaches us.
There really isn't. Like, we
can't
not one of those
travel
things.
faster than light. We can't go out there and check that star and say, oh, look, it died. Let's go back to Earth and wait 200 years and then watch it. We can't do that physically. We just can't travel that fast.
Yeah, it is that one rare case. It's not. It's like, I don't know where I'm going. It's that one time where it could happen. And if you look at all the stars that you can see with just your eyes, it's the only one that shows any sign of being near dying.
It's true. And in fact, on that note, there's a great image that was taken of Betelgeuse with ALMA, the Atacama Large Millimeter Array. And it's a direct image of Betelgeuse.
I haven't seen this picture. I'm Googling it right now.
You should. It's pretty amazing. It comes up when you just type in Betelgeuse. But it shows the kind of the blobby texture of Betelgeuse, and that's what you expect of a star that's unstable, that's getting ready to explode as a supernova. Is it's outputting so much heat, it's kind of roiling, it's boiling, and reaching the end of its life, and it's got this crazy shape, and it's amazing that we can actually image that to begin with.
Yeah, ALMA's a pretty crazy telescope. It's able to. Because it's an array of scopes, it's an array of radio dishes, and it gives you a really high resolution. I'm looking at this picture now. Yeah, that's how you know it's going to die, because it's not a spherical anymore. It's not happy. It's not sitting in a perfect hydrothermal what's the word I'm looking for? The pressure one.
No.
It's not in equilibrium anymore.
Okay, we're thinking of two fancy words for this, I think. But so. Okay, so we've covered now the really weird one of Betelgeuse. And Betelgeuse is a large star, too. I mean, to begin with, it's not going to live a long time.
True, yeah.
Right, so even though, and I'd say maybe 500 million years, it's outputting a huge amount of energy. It's way bigger than the sun is, and still not as much as a blue supergiant, but it's definitely going to live a lot shorter life than the sun does. So, I mean, if we say 500 million years, and we're getting to the end of that 500 million years, again, the odds of its death throes being right around when, like now, that 600 light year window, or 600 year window, it's really slim. But I want to talk about one other star.
Yeah.
And I don't think this is a visible star, but it's interesting anyway, is Eta Carinae.
Oh, it's visible in the south, I think.
Is it visible?
I'm going to Google it right now. It's in the southern hemisphere. I know that for sure.
Yeah. I think it's visible. I'm not sure, which is, it's good we check this, but the interesting thing about Eta Carinae is that it is absolutely in its death throes. It's undergone small nova flares, right? It's expelling material right now. It's getting ready to blow up as the brightest supernova in history when it does go.
That one, it's 6.345, 6.3 or 4 or 5 apparent magnitude, meaning it's just past what the eye can see. So sorry, can't see it right now.
Oh, okay, but for argument's sake, because that star is what we would call pretty much dead, like ready to blow up tomorrow.
Okay.
If we bring that in to the conversation, we still don't know if that one is going to die tomorrow or 1,000 years from now.
Yeah. So that's another. We don't really know what triggers the end, right? Like we know that the reason a star dies is because it runs out of enough fuel at its core to sustain fusion, which keeps it afloat. And as soon as the internal pressure stops, the star collapses, and then it explodes, and then that's the end of the star. Well, depending on the size, but in general, the idea is that it runs out of fuel, and we just don't know what's the cutoff point. Like, is it how much fuel left can sustain the star, and we can't just predict by looking at a star how much fuel it's gone through and how much is left, and when that tipping point will be. So even this one that's right on the edge, Eta Carinae, is right on the edge, and it looks like it's going to explode, but it could be another 1,000 years before it does.
That's true. Have you ever seen that animated GIF of it?
No.
It's really neat because it's only over the last 20 years that they've been taking pictures of. It's actually forming a nebula called the Homunculus Nebula.
Do I Google animated GIF or animated GIF?
Oh, well, it depends on how you spell it, right? It's a GIF. Let's be honest. We're not heathens here. It's a GIF. So, yeah, the animated GIF of it is interesting because you can actually see the growth of the Homunculus Nebula. I mean, you need a telescope in order to see that, but you get in close enough, and it's like, yeah, these lobes of material are actually being spewed out of this star that's shrouded in this veil of gas. And as it's expanding, you can actually see that and on reasonable timescales, which is kind of cool. And I mean, that's the stuff that we're really interested in as astronomers when we're talking to the public, because it's something that's on that human time scale.
That is crazy. I just looked at it. It is, you can actually, with data over the last 20 years or so, yeah, you can see it actually expanding, the nebula around it. So
which is really fascinating. Yeah.
Let's take a look at, if you went out, let's sort of bring it back a little bit. If you went out and you looked at the stars, those stars are between 4 light years away to maybe a few thousand light years away, and those are the closest ones to us. The galaxy itself that you live in is about 100,000 light years across, meaning that even if you could see, which you can't, but even if you could see with your eyes the furthest star in our galaxy, it's only 100,000 light years away, meaning that it's unlikely that it's died in the 100,000 years that the time that the light has taken to get to you, because stars live just much longer than that.
Yeah. So even if you include all the stars in the galaxy, just you've heard the estimate of supernova explosions in the galaxy, right? There's half a trillion stars in the Milky Way?
Yeah, something like that.
Is that too high? Is that too high? I don't know. Anyway, I mean, we're rounding.
Yeah.
We're rounding here. So,
yeah.
So 300 to 500 billion stars in the Milky Way. And the estimate is roughly that one of those stars should explode as a supernova every year.
Yeah, that's pretty low.
which for that many stars is really low. And so
really low.
Yeah, but then the next question is, well, hey, if that happens, why can't we see them die? Why can't we see them explode? And we've already answered part of it in that, some of them are so far away that even when they do explode, it takes a long time for that light to reach us. So, I mean, that's kind of an average estimate. And the other part is that because we're in the galaxy, we can only really see a very small portion of it. And this is probably something to get into in another episode, but all the stars in the sky that we see it's just a tiny fraction of all the stars in the galaxy. Right? So I think that's another episode or another thing to get into.
That's a whole that's a whole thing.
It's a whole other can of worms. And we've talked a few times about going down other paths and opening up many cans of worms in different directions, which we'll do. But it's good to stick to this question and kind of temper it a little bit. So we've got all these supernovas still happening. They take a long time. They're incredibly far away. Even though we should see one every year, on average, we haven't. The last star death that we witnessed was 1987, right? Supernova 1987A. And that wasn't even in our own... Yeah, that wasn't even in our own galaxy.
That was the Magellanic Clouds?
Yeah, that was in the LMC, Large Magellanic Clouds. So the last one that was apparently seen in our skies was in 1611. I think that was Kepler. Might have been after that, because I know there were a couple around that time. Tycho Brahe saw one, apparently. Mm-hmm. So, I mean, that's 400 years when we're supposed to have one every year, roughly. So it's something interesting to think about. But I mean, let's bring all this back together. What have we covered so far?
Well, I've learned that supernovas happen more often, because I didn't know that I knew a rough idea, but I didn't realize that it was once a year we should have one in our galaxy.
No, that's on average, yeah, and that's in the galaxy. So, like we said, it doesn't take into account the distances and the half the galaxy that we can't see, and because of the fact that we're in the galaxy and, all that stuff, and the dust and everything. But yeah, even with those big numbers, we learned that.
We know started with the question of when I look at the stars, are they already dead? And the answer is, well, not really, but maybe.
on a very small, it's a very, very unlikely chance. Probably as likely as me winning the lottery tomorrow. So, and I didn't buy a ticket, so,
that's there you go. Very small.
But, yeah. So pretty much the stars are not dead. You're not looking at ghosts in the sky, but what you are doing is you're looking back in time, right? So, I often say this to kids when I'm talking about seeing into the past, right? It's just like we were talking about earlier with the sun. If you were on the sun and took a selfie and sent it over to me here on Earth, it would take 8 minutes for that picture to arrive.
How many selfies do you take?
Probably one a year at this rate.
Right.
Mostly my phone takes pictures of cats. So, but so one a year. So if I take my one annual selfie and I send it from the sun to you, it takes 8 minutes to get there, which is not bad. And when you get it, you see me 8 minutes ago, which is pretty current. But if you're on Alpha Centauri at 4 light years away, and you take a selfie and you send it to me, now that data, that information is traveling at the speed of light, because that information is electromagnetic radiation, and it's traveling, and it takes 4 years to get all the way to me. And so after 4 years of not hearing from Jesse, probably more than that,
it's like regular life.
Yeah, right. Pretty much. I get a text that's a selfie of Jesse, and I say, "Oh man, he looks so young," and that's because he took that picture 4 years ago. That picture is of him, how he looked 4 years ago.
How much are you expecting me to age in 4 years?
It depends on which 4 years, I suppose.
I guess.
So even though the stars aren't dead, they're all still alive, we're looking at them as they looked in the past. We're never seeing the present.
You know what? I think the question. So, I think about this question, and I see it in I said it before. I hear it in pop culture. I hear my friends say it that aren't in the know, like you and I, and it makes me cringe a little bit. But now that I think about it, I feel like the question actually does have an inkling of the right substance. Like you're saying, it is it is the question or the statement of saying, hey, you look at those stars, they're not there anymore. It is saying and appreciating that the universe is very big and it takes time for light to get places. It's missing the piece of information that says how long a star lives and the likelihood that it would die in that time as it traveled. So I actually am pretty proud that people would recognize that it takes time for light to go that far. That's actually a pretty cool thing to know for people to know.
It's kind of like that statement, no press is bad press, right? And obviously there is bad press when you get things completely wrong or somebody completely misinterprets you. But in this case, what I'm getting at is that it's great that people are talking about this kind of thing, that they have the kind of reverence about the universe to be like, whoa, it's like we're looking at ghosts. Well, no, but it's even cooler than that. You're looking back in time with your eyes. You're time traveling as you're looking at the stars. I think that's way cooler.
Yeah, it's always fun to talk about like stars that are, say, 70 million light years away, and if those stars had planets and those planets had a telescope and they looked at Earth, they would see the light that left Earth 70 million years ago, and that would be dinosaurs, right? So like, it's just the universe is so weird. You look back in time when you look out into space.
It is, and the last, and you can even extend that further, right? You get out to 13.7 billion light years away, and at that point, there's no more universe, right? It just didn't exist, and so if you're at that distance, you're seeing the beginning. But again, that's
studying space for 10 years, and that still really bends my brain a lot. I still can't quite comprehend it. You know what we should do an episode on is co-moving versus non-co-moving coordinates in the universe. That's a whole can of worms, because the universe, we talk about it in terms of like 13.8, whatever the number is, 13.8 billion light years in size. But the actual number is a little different depending on the frame of reference you're measuring from. It's really interesting.
I feel like we need visuals for that one.
Yeah. We should make our first ever video.
This is the first episode of the podcast.
Yeah. Right? Although I think we answered the question.
I think we did. So what do you want to talk about next week?
Oh, I don't know. I don't know how many cat pictures Ryan has on his cell phone.
That's a good question.
Infinite. It's the definition of infinite.
So yeah, I don't know. We've come up with quite a few questions. There's been some pretty interesting news the last couple days about the gravitational waves.
Oh, let's do gravity waves. Oh,
yeah.
Let's just talk about gravity waves for.
Well, and I'm going to tease you that I'm going to tease you here. Gravity waves are something completely different than gravitational waves.
My bad. I knew that.
But let's leave it at that.
Okay.
Because I think next week we can explain that.
All right.
And let's say they're not gravity waves; they're gravitational waves.
Indeed.
But yes, enjoy the ghosts in the sky.
Well, that's the end of this show. Thanks for listening.
If you want to get in touch, find us on Twitter.
My handle is @JesseRogerson.
And my Twitter handle is @AstroInAction. Check out other episodes, or just keep listening to us every week.